Okay, let's have a look at this CIE Physics A-Level Paper 4 then. Question 1. The Earth may be considered to be a uniform sphere of radius 6,380 kilometers with a mass of 5.98 times 10 to the 24 kilograms concentrated at its center as illustrated here. A mass of 1 kilogram on the equator rotates about the axis of the Earth with a period of 8.62 times 10 to the 4 seconds. Calculate to 3 significant figures the gravitational force of attraction between the mass and the Earth. So we know that force is gmm over r squared. So that's going to be 6.67 times 10 to the minus 11 times the mass of the Earth times by 1, so we can forget about that, divided by the distance between them. That's going to be 6.38 times 10 to the 6. That's our 6,380 kilometers. Make sure you put it correctly into your calculator. That gives us 9.799 to 3 sig figs. We need to round that up to 9.80. Sounds familiar? Part 2. Calculate the centripetal force Fc on the 1 kilogram mass. Well, we know that centripetal force is F equals mv squared over r, but we don't have v in this case. Instead, we are given a time period, so that lets us find the frequency. So let's put angular frequency in there instead. So you should remember that v equals omega r, so that's angular frequency there. So let's put that in. M omega squared r squared over r. So that gives us m omega squared r, and that is equals to m times r times 2 pi f all squared, but we have time period instead, so it's going to give us m r 4 pi squared. Just squared that. We're going to put time period on the bottom because, as we know, time period and frequency are reciprocals of each other. Okay, so that's going to be 1. We can forget about that. So let's take our radius again. 6.38 times 10 to the 6, 4 pi squared, divided by 8.62 times 10 to the 4 squared. That gives us a centripetal force of 0.0339. Again, if we go into 3 significant figures. Part 3, the difference in magnitude of the 3 forces. So it's 9.80. Take away 0.03 gives us 9.77. Finally, by reference to your answers in A, suggest with a reason a value for the acceleration of free fall by the equator. It will be 9.77 meters per second squared. Because this is Newton per kilogram, that means that we have found a value for the resultant force on each kilogram, and that is the same as acceleration due to gravity. Question is, why isn't it the full 9.8? Let's say that the Earth wasn't spinning at all, then that would mean that we would have the full 9.8 newtons pulling down. But because everything on the Earth is spinning, and at the equator they're spinning faster, that means that they want to, as it were, fly off. So in order to achieve that full 9.8 newtons pulling down, that would mean that we need an extra force, but we don't have that. So instead, what happens? The actual acceleration decreases. So yeah, that does actually mean that you feel lighter at the equator than you do at the poles. So if you struggle with that, then have a look at my fields lesson video. Question 2, the volume of some air assumed to be an ideal gas. The cylinder of a car engine is 540 at a pressure of 1.1 times 10 to the 5 at a temperature of 27 degrees. The air is suddenly compressed to a volume of 30 centimeters cubed. No energy enters or leaves the gas. By heating during the compression, the pressure rises to 6.5. Determine the temperature of the gas after compression. Alright, so we know that PV equals nRT, but because we have the same amount of gas, then N and R are constants, so that must mean that we are looking for the second temperature. So let's rearrange. We end up with T2. I'm just going to swap those over. P2 V2 divided by P1 V1 times, I'm going to take T1 over the top as well, times T1. Let's put those numbers in. So 6.5 times 10 to the 6 times 30. We can just leave it as centimeters cubed because we just have a ratio, times our temperature. It's not 27 because it needs to be in Kelvin. So in Kelvin that would be 273 plus 27. So that gives us 300. Nice round number for us. Divided by the initial pressure times the original volume. Okay, big calculation. Again, make sure that you put it correctly into your calculator. That gives us a temperature of 985 Kelvin. So the first law of thermodynamics, just something you need to remember. Delta U equals Q minus W. In other words, energy change of a system equals the energy in minus the energy out. Use the law to explain why the temperature of the air changed during the compression. Because there's no energy change in the system that's just been described, that means that Q is 0. There's no heat going in or out of the system at all. So that must mean that the change in energy equals to the work done. Forget about the minus because we are just talking about a change. So because we are compressing it, that means that delta U increases because we are doing work. And if the energy of particles increases, then so does the kinetic energy and therefore temperature of system. If you struggled with any of that, especially the first bit, I want to know where I got that from, then have a look at my gas laws video. The defining equation for simple harmonic motion is A equals minus omega squared x. State the relation between omega and frequency f. Omega is angular frequency. It's not how many full cycles, but how many radians per second. Part 2, state the significance of the negative sign in the equation. Well, one of the conditions needed for SHM is that acceleration is always opposite direction to displacement. Otherwise, it's not going to go back and forth. It's just going to fly off. B. A frictionless trolley of mass m is held on a horizontal surface by means of two similar springs, each of spring constant k. The springs are attached to fixed points as illustrated in figure 3.1. When the trolley is in equilibrium, the extension of each spring is E. The trolley is then displaced a small distance x to the right along the axis of both springs. Both springs remain extended. Show that the magnitude F of the restoring force acting on the trolley is given by F equals 2kx. So let's just take it one step at a time. Let's take this one spring here. Its force, its restoring force, if it's been moved to the right here, the trolley, then obviously this spring has extended even more. So that means that the force is no longer KE, it's actually KE plus X. So that's the total extension. What about this one? Well, it's KE minus X. So that's the individual forces, but they're pulling in opposite directions. Therefore, the total force is going to be equals to KE plus X minus KE minus X. You could probably see that the E's are going to cancel because we're minusing them, and we're going to end up with F equals KX minus KX. So that gives us 2KX. So, bit tricky conceptually, those kind of questions, but you just got to think what are the forces individually, then find the resultant. Part 2, the trolley is then released. Show that the acceleration A of the trolley is given by this. Easiest question ever. We know that force is mass times acceleration, so therefore acceleration is force divided by mass. Technically, yes, the acceleration is pulling in the opposite direction to the displacement, so actually I don't know why they haven't got a minus in there. They should do technically, so that's just going to give us 2kx over m. Really weird question, don't know why they'd give 2 marks for that, but there you go, easy 2 marks. Okay, last bit. The mass m of the trolley is 900 grams and the spring constant is 120 newtons per meter. By comparing the equations in A and B, determine the frequency of oscillations of the trolley. So we know that our bog standard equation for acceleration is minus omega squared x, and obviously that is minus 2 pi f squared x. But we also figured out here that acceleration is minus 2kx over m. So when they say compare, they really mean equate the two equations for acceleration. So what do we see? We see that the minuses cancel out. We see that the x's cancel out. We want to find frequency, so let's take frequency squared. So that gives us 2k over, we're going to take the 2 pi squared over the other side. That ends up being 4 pi squared m. And so that cancels down to just k over 2 pi squared m. And that gives us 120 divided by 2 pi squared times 0.9. Because we need our mass to be in kilograms. We're going to do the bottom bit first. 2 pi squared times 0.9, 120 divided by that answer, that gives us 6.75. Square root of that gives us the frequency. That ends up being 2.6 hertz. A sinusoidal wave of frequency 75 kilohertz is to be amplitude modulated by a wave of frequency 5 kilohertz. Explain what is meant by amplitude modulation. So we have a carrier wave, and then we have our signal wave, our information signal that comes in, and it changes, it modulates the amplitude of the carrier signal. Explain what is meant by amplitude modulation, therefore. The amplitude of the carrier wave or signal is varied by the displacement of the information signal. On the axes of figure 4.1, sketch a graph to show the variation with frequency f of the power p of the modulated wave. Label values on the frequency axis. Okay, so we have one line going upwards. That's going to be our carrier frequency, that's 75 kilohertz. And we can see that the frequency of the information wave is 5 kilohertz. Therefore, the upper and lower bounds of this band are going to be 70 and 80. Therefore, the bandwidth of the modulated wave, 70 to 80, is 10 kilohertz. Nice and easy. Okay, question 5. A microphone is connected directly to an amplifier having a gain of 63 decibels, as shown here. The microphone and amplifier are connected to a receiver by means of a wire pair having an attenuation of 10 decibels per kilometer. The power of the output signal from the microphone is 2.5 microwatts, and there is a constant noise power in the wire pair of 0.035 microwatts. Explain what is meant by noise. Noise is unwanted energy that affects a signal. B. Calculate the power output of the amplifier. Gain or attenuation in decibels is equals to 10 times log to the base 10 of power out divided by power in. Now we saw that we had 63 decibels. We're trying to find out the power out, and the power in is 2.5 microwatts, because that is what is going into the amplifier. So therefore 6.3, because divided by 10, equals log to the base 10 of power out by that. In order to undo a log to the base 10, we need to do 10 to the power of that number. So 10 to the power of 6.3 will give us power out divided by 2.5 times 10 to the minus 6. Therefore, power out is equals to 2.5 times 10 to the minus 6 times 10 to the 6.3. That gives us power output of 4.99 watts, or 5 watts to 2 sig figs. Also, just taking the shortcut with the calculation, times 10 to the minus 6 times 10 to the 6.3 gives you times 10 to the 0.3. So you could have just done 2.5 times 10 to the 0.3. That would have also given you 5. Calculate the length of the wire pair for the signal power to be reduced to the level of the noise power. Okay, so we do want our attenuation in decibels first. Again, that's equals to 10 times log to the base 10 of our powers. And we have 5 watts here. And we want to compare that to the noise power, which is 0.035 microwatts. That's 3.5 times 10 to the minus 8 watts. That gives us an attenuation of 81.5 decibels. And we know that each kilometer results in an attenuation of 12 decibels. Therefore, length of wire is going to be given by our total attenuation divided by the attenuation per kilometer. That gives us 6.8 kilometers. Fairly tricky question, but it's just a matter of realizing what goes into your power in and power out here to calculate the attenuation. Question 6, state the relationship between electric field strength E and potential V. So if you don't know where I'm getting this from, then have a look at my fields video, because field strength and potential and force and potential energy, they all work together, they all fit together. And you find out that electric field strength is all to do with how the potential varies with distance. In other words, field strength equals the potential gradient. That's what we call it. That goes for gravitational fields as well. 2 positively charged metal spheres, A and B, of diameters 18 and 12 centimeters respectively, are isolated in space. Bless them, as shown here. The centers of the spheres are separated by a distance of 50 centimeters. Point P is at a distance x from the center of sphere A along the line joining the centers of the 2 spheres. And over the page again, state qualitatively and explain the variation with distance of the force on a proton placed at point P, where x varies from 10 centimeters to 41 centimeters. So let's just have a look here. We just said that field strength is equals to the potential gradient, and here we do have the potential gradient. So the gradient of this is going to equals the field strength. And don't forget that that is force per coulomb of charge. And we're being asked to explain the variation with distance of the force on a proton. So where do we have the greatest gradient? We have it at this point here. So we are going from 10 to 40. First thing we say is gradient of graph equals field strength. This is greatest at x equals 10. Therefore, force is greatest at this point. Which way is the force going though? Well, we can see that both of these are positively charged, so the closer it gets to A, the more it's going to be repelled away from A. Direction is towards B. It's being repelled or repulsed from A. What next? What happens as the distance increases? We can see that the gradient decreases to 0 at 35 centimeters. So as x increases, force decreases to 0 at x equals 35 centimeters as gradient equals 0. Finally, it increases again above x equals 35 as force is now towards A due to opposite gradient. It is now positive at this point instead of negative. So there you go. The key to this question was remembering that field strength is not only newtons per coulomb, it is also volts per meter. It's the potential gradient, very important. And then when you look at the graph, realizing that it is the gradient of the graph that gives you the electric field strength. Like I said, if you're struggling with this, then have a look at my fields video, which hopefully clears things up a little bit. Question 7, all to do with electricity. Symbol for an LED is shown here. On figure 7.1, mark the polarity of the diode such that the diode is emitting light. The arrow shows the direction of current, that is conventional current, so it has to be positive going to negative. The circuit diagram for a temperature sensing device is shown here. It looks very complicated. It's not that complicated. The operational amplifier op-amp is ideal. Some values for the resistance of the thermistor at different temperatures are given here. The thermistor is held in a water bath at a temperature of 15 degrees, so we're talking about a resistance of 2200 ohms. Determine the voltage at A. Okay, so nice and easy. We can see that 9 volts is available for these two resistors to share. They are of equal resistance, therefore we know that half of the 9 volts is going to get used up by each, so it should be 4.5 volts. At B, well, we can see that the resistances are 2200 ohms and 800 ohms. We know that the 2200 ohms of the thermistor is going to get a greater share of that 9 volts. We know that 800 ohms is going to get a lower share of the 9 volts than the 2200 ohms. So to find it, all we have to do is take our 9 volts, times that by the ratio of the resistance compared to the total resistance. That gives us 2.4 volts. At the output of the operational amplifier. Okay, so we have 4.5 volts going into the negative terminal, 2.4 going into the positive terminal. Now, if the bottom value was a higher PD than the top one here, and that means that the op-amp would give out plus 9 volts, but they are the other way around. So therefore, that means that we get the minus 9 volts out instead. State which LED is emitting light. Well, if we have minus 9 volts coming out of here, that means we have minus 9 volts here. So current is going to flow not from here to here, but 0 to minus 9. Current's going to go up this way. Therefore, it cannot be G that lights up, it's going to be B. Describe and explain what is observed as the temperature of the thermistor is raised from 15 degrees to 100 degrees. So we can see that as the temperature increases to 100 degrees, we end up with a resistance of 680 ohms. That means that this resistor is going to have more than 4.5 volts. Let's calculate it real quick, why not? It's going to be 9 times 800 divided by a different total resistance now. Overall, that's going to be 1480. Gives us 4.9 volts. So now we have 4.9 volts in here. So that means that the bottom voltage is higher than the top voltage, so we're actually going to get plus 9 volts coming out. What does that mean? Current is actually then going to flow down instead of up. So that must mean that G lights up instead. So let's write that all down. VB is now increased to 4.9 volts. Therefore, output of op-amp is plus 9 volts. Current flows down through just LED G. For all my AQA people out there, you do not need to know about op-amps for your A-level. But the rest of the question is still helpful. Question 8, all to do with magnetic fields. A small coil is positioned so its axis lies along the axis of a large bar magnet. Don't really care. We have a cross-sectional area of 0.40 centimeters squared and 150 turns of wire. We may as well convert this now because we know we're going to have to do this eventually anyway. And we have centimeters going into meters, so that must mean that we are dividing by 100. But because we're going from centimeters squared to meters squared, that means that we have to divide by 100 squared, which is 10,000. Therefore, 4 times 10 to the minus 1 centimeter squared is going to be 4 times 10 to the minus 5 meters squared, because 100 squared is 10,000, and that's 10 to the 4. Okay, so we have our area. Nice. All right, now we have our graph of flux density against distance. Let's have a look at what we're being asked then. The coil is 5 centimeters away from the face of the magnet. Use figure 8.2 to determine the flux density in the coil. So 5 centimeters. Bam, that's going to be 50 milliteslas. But look, we're being asked for teslas. That's where they're trying to catch you out. It does seem too easy. So that must mean that it's 5 times 10 to the minus 2, or 0.05. Hence show the magnetic flux linkage of the coil is 3 times 10 to the minus 4 Webers, or Wubs as I like to call them. So flux linkage is N phi, and that is BAN. So that's 0.05, that's our flux density times our area. Already calculated that like a boss. 4 times 10 to the minus 5 times the number of turns, it's 150. Easiest 2 marks you'll ever get. That gives us 3 times 10 to the minus 4 Wub. Now, technically, it should be Wub turns because we're talking flux linkage. State Faraday's law of electromagnetic induction. Induced EMF, this always comes up, so you have to remember this, is equal to the rate of change of flux. Let's put flux linkage, seeing that we are talking about a coil with numerous turns here. Now what's weird here is that the mark scheme says induced EMF is proportional, but we know Faraday's law is delta phi by delta t. That is rate of change of flux, or flux linkage if you put an n in there as well. It is equals to it. Okay, part C, the coil is moved along the axis of the magnet, so the distance x changes from 5 centimeters to 15 centimeters. So we started at 50 and we're going down to 15, so that is 8 milliteslas. So the change in the flux linkage, N delta phi, is going to be AN times the change in the flux density. So that's going to be our area, which we already have from earlier. 4 times 10 to the minus 5 times the number of turns times our difference in our flux density. We started at 50 and we went to 8 milliteslas, so that's going to be 42 times 10 to the minus 3 because it's milli. That gives us 2.52 times 10 to the minus 4 Wubs, or Wub turns. The average EMF induced in the coil, we know that that's delta phi, or delta n phi, if we're dealing with flux linkage. So that gives us 2.52 times 10 to the minus 4 divided by 0.3, because that was the time it took to change. That gives us 8.4 times 10 to the minus 4 volts. Finally, D, state and explain the variation, if any, of the speed of the coil so that the induced EMF remains constant during the movement. Okay, so what can we see here? We can see that here we have a steep gradient, so that equals fast change in B, so that means bigger EMF induced. Here we have shallow gradient, so we have a slow change in B. So if we have our coil here and then we have our coil down here, in order to achieve the same EMF induced with this flux density changing less quickly down here, that means that we have to be moving it faster. Coil must be moved faster the further away from the magnet as X increases, as B changes less quickly. We can say delta B by delta X is less. 9. A charged particle passes through a region of uniform magnetic field, flux density 0.74 teslas, as shown here. The radius r of the path of the particle in the magnetic field is 23 centimeters, or 0.23 meters. The particle is positively charged. State the direction of the magnetic field. Okay, which of Fleming's rules are we going to use? The way I remember it is the motor effect is the left hand because motor cars drive on the left, at least in the UK they do. And generator, because the dynamo effect is involved in generator, so generator. So what is this? This is producing a force, so we're going to be using Fleming's left hand rule. It's the motor effect. So let's just have a think. We have our current is going that way because it is a positively charged particle, and current, your second finger, is the flow of positive charge. The force is going upwards, so my thumb is going upwards, and so that means that the magnetic field is going into the page. Show that the specific charge of the particle is given by the expression this. Okay, when it comes to anything to do with a charged particle in a magnetic field, we have to say that BQV, which is the force on the particle, is equals to mv squared over r. All this is saying is that the magnetic force is producing a centripetal force, making it go in a circle. Cancel the v's down, easy, and then we want to have m over to the other side, so let's pop it over here, and we want b over the other side. Therefore, we end up with q over m equals v over b r, which is what we have there. The speed v of the particle is 8.2 times 10 to the 6 meters per second. Calculate the specific charge of the particle. So q over m, which is our specific charge, is equals to v, which is 8.2 times 10 to the 6, divided by flux density, which is 0.74, times the radius, which is 23 centimeters. That's where they're trying to catch you out, 0.23 meters. Easiest 2 marks you will ever get, though, I kid you not. And that gives us 4.8 times 10 to the 7 coulombs per kilogram. It should be a big number, that's what you would expect. And because it's not an electron, it's something heavier, and electron is times 10 to the 11, this sounds about right. Question 10. The rectified output of a sinusoidal signal generator is connected across a resistor R of resistance 1.5 kiloohms, as shown here. The variation with time t, a potential difference V, is shown here. State how the rectification shown in this figure may be achieved. It's a diode. Strictly speaking, a single one, not a bridge circuit, just one single diode. That makes sure that current can go through one way, but not through the other way. So current's trying to do that, but it can't because it can't go backwards. This needs to be in series with output and resistor R. A capacitor is now connected in parallel with the resistor R. The resultant variation with time t of the potential difference V across R is shown here. Ooh, that looks very smooth, doesn't it? Using figure 10.3, determine the mean potential difference across resistor R. So let's have a look. We're going from 4.8 to 6. So the difference there is 1.2 volts. What's directly in between? It's going to be 5.4 volts. Calculate the mean current in resistor R1. Well, we know that V equals IR. We're trying to find out the current, so therefore current is PD divided by resistance. We said the mean PD is 5.4. Question said that the resistance is 1.5 kiloohms. That means that the average current is 3.6 times 10 to the minus 3 amps, or 3.6 milliamps. Calculate the time in each cycle during which the capacitor discharges through the resistor. So the capacitor is discharging through the resistor from when the PD is at a maximum and it goes down to a minimum. And it looks like this is the same over here, so why not go from here to here? We can from 0 to 0.027 seconds. Using your answers in part 1, calculate the charge passing through the resistor during one discharge of the capacitor. Charge is current times time, so that gives us 3.6 times 10 to the minus 3 times 0.027. 9.7 times 10 to the minus 5 coulombs. And the capacitance of the capacitor. We know that capacitance is the amount of charge stored per unit PD, or per volt. So we have our charge that the capacitor was filled up with, And we have our PD. However, we are not looking for the 5.4 volts here because we have got the charge. This charge here is what it loses in this time. And so we cannot use the total PD. We can only use the change in PD. So just to make it clear, let's put a delta Q and delta V in there because we are not discharging the capacitor completely. So we said that the difference was 1.2 volts, gives us 8.1 times 10 to the minus 5 farads. And last bit for this question, a second capacitor is now connected in parallel with the resistor R and the first capacitor. So if I was to draw it on here, there you go. On figure 10.3, draw a line to show the variation with time t of the potential difference V across the resistor. Okay, so we need to figure out what happens to the capacitance. Now, the rule that I use to remember what happens to the equivalent capacitance is they do the opposite to resistors. So when you have resistors in series, you find the equivalent resistance by just adding them up, and if they're in parallel then you do 1 over the R total equals 1 over R1 plus 1 over R2. It's the opposite for capacitors. So the equivalent capacitance of these capacitors in parallel, we just add them up together. So what happens to the capacitance? Capacitance increases. If capacitance increases, that means that we can store more charge on these capacitors compared to before. That means therefore it's going to take longer to discharge. Similar shape, just smoother. So the more capacitors that you have in parallel, the smoother your rectified DC is going to be. Alright, question 11 to do with energy levels here. The energy bands in a solid are illustrated here. We have the conduction band, the forbidden band, and the valence band. By considering charge carriers and lattice vibrations, use band theory to explain the change of resistance of an intrinsic semiconductor with change of temperature. Let's just take things one step at a time, shall we? So electrons are usually found in the valence band. When temperature increases, the lattice vibrates more, just like a metal. And we can say 0 Kelvin, valence band is filled. The lattice vibrates more, but also electrons gain energy to enter the conduction band. So they are here, and once they're given energy, they end up in the conduction band. This leaves positive holes in the valence band, and charge moves. In the metal, when the lattice vibrates more, that results in a higher resistance. That is the case here as well, but this whole deal with electrons jumping to the conduction band, that outweighs the effect of the lattice vibration. So we can say increased charge carriers outweighs effect of lattice vibrations, therefore resistance decreases. There you go. That's how you explain how an LDR or a thermistor works. When you increase the amount of energy going into them, that's why the resistance decreases overall. Question 12. The quality of an image produced by X-rays depends on sharpness and contrast. State what is meant by sharpness. Sharpness is all about how distinct the boundaries between regions are. So you have a very sharp line where the bone ends, instead of a fuzzy line. What about contrast? That is the difference between light and dark regions. Higher contrast, more blackening, we can say, between regions. A parallel beam of X-ray photons is produced by an X-ray tube with 80 kilovolts between anode and cathode. The beam has its intensity reduced to 1/2 of its original value when it passes through a thickness of 1 millimeter of copper. Determine the linear absorption or attenuation coefficient mu of the X-ray photons in the copper. So the ratio is a half when it goes through 1 millimeter, and that is equals to e to the minus mu. That is the coefficient up here. So taking logs of both sides, log a half equals minus mu, and you should remember that log of half is log 1 minus log 2, log 1 is 0, so that equals mu, minuses disappear, therefore mu is equals to log 2, which I can't remember off the top of my head, and we are talking natural log here, not log to the base 10. Last part, suggest with a reason the effect on the linear absorption coefficient if the beam is comprised of 100 kilo electron volt photons. If the photons have more energy, then of course they're going to go further. Attenuation is going to decrease. So the X-ray photons are more penetrating, mu decreases. Question 13, last question. The isotopes radium-224 and radium-226 both undergo spontaneous alpha particle decay. The energy of the alpha particles emitted from radium-224 is 5.68 megaelectron volts. Radium-226 is 4.78 electron volts. State what is meant by the decay constant of a radioactive nucleus. So the decay constant is lambda. That is the probability of a nucleus decaying per unit time. And that's per second. So it has the units s to the minus 1. Sure, it can be minutes to the minus 1, it can be hours or years to the minus 1 as well. Part 2, suggest with a reason which of the two isotopes has the larger decay constant. Well, which one has the bigger energy alpha particle being released? It's radium-224. Radium-224 emits alpha particles with higher energies. Therefore, it is more unstable. Therefore, more likely to decay. Therefore, has a higher decay constant. Radium-224 has a half-life of 3.6 days. Calculate the decay constant of radium-224, stating the unit in which it is measured. So seeing that we've been given the half-life in days, we may as well stick with days. Calculate the decay constant. You don't need to derive this, but if you can't remember how to calculate the decay constant from half-life, this is how you do it. So we have n over n0 equals a half. That's how much the radioactivity and the number of radioactive nuclei has decreased. That's going to be equals to e to the minus lambda t. Take logs of both sides, log a half, which is equals to log 1 minus log 2. And of course log 1 is 0 again. That equals minus lambda t half if we are talking about the half-life. Minuses disappear, so therefore we end up with a decay constant of log 2 over the half-life. So that's log 2 over 3.6 days. Be careful with your brackets with this one. And we end up with a decay constant of 0.19 to 2 sig figs. What's the decay constant? Well, we calculated it using days, so therefore our decay constant has to be days to the minus 1. Determine the activity of a sample of radium-224 and mass 2.24 milligrams. We know that the activity is equals to minus, forget about the minus, lambda n. So we have our decay constant. So we need to find out the number of nuclei that we have. So the first thing we need to do is figure out how many moles we have. Okay, so we know that 1 mole of radium-224 has a mass of 224 grams. Therefore, the number of moles that we're going to have, little n, is going to be 2.24 times 10 to the minus 3, because we want this in grams and this is in grams. So that's the same as saying 2.24 times 10 to the minus 3 divided by 2.24 times 10 to the 2. These disappear, we end up with 1 times 10 to the minus 5 moles. Times that by Avogadro's, and we end up with the number of particles that we have. All we have to do is take away 5 from our power there, so 6.02 times 10 to the 18 nuclei. Therefore, the activity is going to be 0.19 times 6.02 times 10 to the 18. we end up with an activity of 1.14 times 10 to the 18. However, that is not counts per second, which is what becquerel is, so we need to turn this into counts per second instead. We want a smaller number, so we're going to have to divide by 24 and 3,600, 24 hours in a day, 3,600 seconds in an hour. That gives us 1.32 times 10 to the 13 becquerel. So that's it for this CIE specimen paper 4. Hope you found that helpful. Please leave a like if you did. Go back to the channel and have a look at my other playlists to find other CIE papers there.